So far, we focused on calculating the probability under one set of conditions. But what's perhaps more important is determining the probability over a wide set of conditions. In order to visualize the probabilities in a very coherent manner, what we could do is we could look at a distribution function, or we could calculate a distribution function, right? And so, when we say distribution function, what we're describing is the probability of some sort of scenario as a function of a variable I, right? Such that if we summed up our probabilities as a function of I for a range of I equals 1 to t, right? So t is you can think of it as the number of categories, right? The totality of these probabilities would just be equal to 1, right? So the sum of all your probabilities needs to be equal to 1. All right, in the case that we're only dealing with sort of two categories of outcomes, so for a case where there are only two categories of outcomes, we can model our probability distribution using what's known as the binomial distribution. So the distribution can be modeled using the binomial distribution. Okay? And so our binomial distribution, which could say is Pn, so some n indistinguishable objects for big N number of total objects, it would be equal to this. Big N there. And then we would multiply it by this. Okay? Right, and you may recognize the form of this binomial distribution, or at least the different terms. So here, this first probability we're dealing with is just the probability that event n occurs, I'll say. And then 1 minus p here is the probability that the other event occurs, the other category, right? And here, we're raising this one to the power of n, because that's just the number of outcomes for this. And then n minus n is the number of outcomes for the other category. And then here, this is where we have the binomial coefficient to account for, make sure that we're not double counting our results. Right, so this is what the result looks like. All right, but to get a better idea of what's going on, we could actually just look at a plot of the probabilities for different cases, right? And so here, what we're looking at is, we're going back to our coin flipping example, where we've flipped a quarter 4 times, and we want to count the number of times that heads shows up in that ensemble of 4 different quarter flips. So the number of times that n, or the head, shows up in that 4 quarter flips, we'll call n sub h. All right? And so if we use the binomial distribution probability function, we could calculate the number of times that 0 heads would show up, right? And that's a fairly rare sort of event, so its probability is low. The number of times that 1 heads shows up, right, its probability is higher. And then the probability that 2 heads show up is the highest, right? And then, after we reach this peak here, then the probabilities start going back down, right? And so we see that, according to the binomial distribution, if we flip the quarter 4 times, then the most likely outcome is that within that 4 quarter flips, we should expect to see heads show up 2 times. Of course, that's just based on the statistics. in actuality, if you did this experiment, you could observe heads showing up 4 times or 0 times. Those are all possibilities, but the most probable one, the most likely one, is 2 heads showing up. Alright, so that's for the case where you're just dealing with 2 categories of outcomes. But we could be more general. For the case where you have T categories of outcomes, where there are T categories of outcomes, then we could use what's known as the multinomial distribution. Multinomial distribution applies. Alright, and so in this case, we would have n1, n2, dot, 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 all the way up to nt, right, comma, big N. And it would look like this. Dot, 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 pt raised to the nt. And then we have our multinomial coefficient. N2, dot, 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 nt. Okay? Alright, and so here, for our distribution functions, we're considering the case where, we're calculating discrete values, right? I is equal 0, 1, 2, 3, or 4. Right? But, for cases where, the x-axis is a little bit more fine, we could actually calculate a continuous distribution function. Distribution functions can also be continuous. Okay? Alright, and so perhaps one of the more famous, or the most famous, continuous distribution function is the Gaussian distribution. So here, we're using x as our variable, and so we would refer to this p of x as a probability distribution. Okay. So this probability distribution, we would say, let me move this to the left a little bit. Okay. So this probability distribution would be equal to this. Sigma 2 pi, the exponential of -1/2 x minus mu divided by sigma squared. Okay? Alright, where mu is your sort of average, and sigma is a standard deviation. And we'll talk more about those later. Alright? But when we're dealing with a continuous distribution function, right? Earlier I said for the discrete one, the sums of the probabilities needs to equal to 1. When we're dealing with a continuous one, there still is a constraint, right? It's kind of similar, all your probabilities need to add up to 1. But since we're dealing with a continuous function, rather than just a straight sum, we're actually going to deal with the integral. So the integral of our probability distribution, or probability density, actually, that's what I should call it. The integral of our probability density between 2 limits should give us exactly 1. Okay? Alright, so that's the case for what we call a normalized probability density. And this coefficient out here, this is important because it helps make sure that this integral is going to be equal to 1. Right? But there are cases where you're going to deal with a non-normalized probability density. So sometimes probability density is not normalized. Okay? So in this case, instead of p of x, we would say we have some sort of g of x. Right? And if we integrated it from our two bounds, because it's not normalized, we would end up with some sort of value that's not equal to 1. Okay? And that's, okay. But, it's actually in the end not a big deal, because we could convert to the normalized probability density fairly easily just by taking our g of x and dividing it by g naught, such that the function would look more like this. A, b, g of x, dx. Okay? Alright, and so this is how you convert a not normalized distribution function to a normalized one. And this is something, or at least this sort of concept or this sort of mathematical form, is something we're going to see quite a lot, especially when we start dealing with statistical mechanics.